So today we are going to talk about the quantized electromagnetic field and states of the electromagnetic field, and then we will talk about photo detection in this quantum picture. So what I've done is, since the quantization of the electromagnetic field is really something that you might have seen in other classes as well, I decided not to go through the math here in the lecture. It's something that you need to see one time, but it's not necessarily something that you'll be using or needing to know from a sort of even from an application perspective very regularly. You need to see it once so that you know how it was done. And so what I've done is just give you the handout that goes through the math of how to quantize the electromagnetic field. And it's not as straightforward as one would think, because that there are some issues with things like the vector potential. I noticed this on the next page. On the second page, you'll see that I say, although the steps seem straightforward, there are a couple of tricky steps along the way, and I've tried to highlight what are the tricky steps in the handout. You'll see that a couple of the tricky steps happen because the A, K, lambda, which are the coefficients of the vector potential, are complex numbers, and in the end we want something that's if we want to make it look like a harmonic oscillator. So you'll find that the Hamiltonian for the field looks like something like p dot squared plus omega squared q squared, but those a in this case it's ak lambda dot, right? That's the vector potential's coefficient derivative, and that derivative is not real, it is complex, right? Because that's how we chose the vector potential. So that's a tricky part, but we get around it by introducing the real and imaginary parts of the vector potential coefficients, and then we proceed through the math, and then you have to worry about the domain of integration, and so on and so forth, but in the end, it is done, right? So that's what you need to know, at the end, we do get a Hamiltonian and a set of operators for the vector potential that look just like for a harmonic oscillator. So at the end of the day, what we get, the result of all of this, is that the vector potential A of r comma t is written as sum over k and lambda square root h bar 2 epsilon naught omega k v times a k lambda p plus a dagger minus a lambda of p times the polarization times e to the I a dot r. Okay, and the Hamiltonian, which you show, or we don't show, but we find that it can be written as h bar omega k a k lambda dagger equal number plus 1/2. And the A of RT, instead of writing it with this minus k lambda, we can make, since we are summing over all k over here, we can take in the second term k going to minus k, and then it looks a little bit more familiar maybe. So this is equivalent by that transformation to sum over k lambda square root h bar 2 epsilon naught omega kb times ak lambda epsilon k lambda e to the I k dot r. And now to find out the electric and magnetic field, so this was the vector potential A, and as I noted at the beginning, this is the Coulomb gauge. So once you have the vector potential, then you can find the electric and magnetic fields. But knowing the vector potential, we need to know the time dependence of the operators A, K, lambda, right? This is in the Heisenberg picture, right? So in this Heisenberg picture, the operators are revolving, and to find the derivatives, then we need to know this ak lambda of t, which we can find from the Hamiltonian, because in the Heisenberg picture, d over dt ak lambda is equal to 1 over ih bar ak lambda comma h, right? Commutator with h, which we can easily show is simply minus I omega ak lambda. So therefore, ak lambda at time t, the operator is ak lambda at time 0, which is the Schrodinger operator, times just a phase factor that goes like that. So I substitute that back in here, and then now I can find the electric field. The electric field is simply minus dou A over dou T. And once I substitute this guy back into there and then take the time derivative, I will find that, again, I'm skipping all these steps, they're fairly straightforward. There's a summation k lambda. Now, because of the derivative, I'll be pulling down factors of I. So that's over here. That's it. So this is the electric field in the quantized operator picture, or in the quantized electromagnetic field. We have that the electric field of the in this quantized picture will have these terms, which are ak lambda and ak lambda dagger, which are just reminiscent of the harmonic oscillator. And in addition, it depends on. So these are all vectors, the unit vectors, and that give you the these polarization of the electromagnetic field of the photon. Okay, so now you might notice this factor of I out in front, and that came from the fact that E is given by the time derivative of this operator. But if you go and look at many textbooks, you'll find that their definition of the electric field does not contain this factor of I. That is just because of a simple redefinition of these operators, right? So all you do is, if you want, you can think of it as a unitary transformation or just redefinition, whatever you want to call it. So they just say that ak lambda nu, the new operator is I, ak lambda old, which is over there, and of course then ak lambda dagger nu is minus I ek lambda whole. So that's just a unitary transformation. Of course, you need to check all the usual rules, which is that you need to show with these definitions that H is still given by H bar omega k summation over k lambda of ak lambda dagger ak lambda plus half, which you can obviously see from the fact that this is I at minus I, that will still remain the same. And also you need to check the commutation relation that these new guys satisfy ak lambda new dagger is also still identity operator. Okay? In fact, you can change to any phase factor you want, really, right? Instead of just I, you're going to put e to the I theta over there. But theta is some arbitrary variable. In fact, that will be interesting later on when we consider things like squeeze states and coherent states and stuff like that. But so with this new definitions, or whatever you want to call it, unitary transformation, now our E of R comma T is simply summation k lambda H bar omega k over 2 epsilon naught b. I once again took the e to the I lambda, e to the I omega t, I took it into the variable definition for ak lambda of t, because as we'll see, there might be situations where the Hamiltonian isn't quite so simple and you may have some other dependence of ak lambda of t, but in general this should be our definition. And in fact, it's nice to separate this out into two parts, which are often called the positive frequency and the negative frequency parts. That is, I write it as E plus of R comma T plus E minus, and these are operators of, oh, did I skip the, I guess I skipped the polarization, sorry. So I call this the positive frequency part, and the reason I call it positive frequency part is, and this is confusing, that ak lambda of t goes as ak lambda of 0 times e to the minus I omega t. Okay, so that is called the positive frequency term. Okay, which is over here, which I know it can be a little confusing, but I'll just point that out here. So e plus of R comma T, right? Or maybe I should write it over there because I don't want to. It's important. So here's this. E plus the positive frequency part of the electric field operator is summation k lambda okay. And so this ak lambda now, this is at 0, and we see that the positive frequency term goes as the e to the minus I omega t. Okay, that just what we call positive is how it circles. As time goes on, it circles counterclockwise in the phasor plane. So that's why we call it positive frequency in this thing. But it's a little confusing that it goes with the minus sign on this term. But that's the reason for it. And you can easily see that E minus, right, is simply E plus dagger. Okay. So it's a little, again, the notation gets a little confusing because there's this plus sign, and then there's a dagger, which is the Hermitian or the electron operator. Okay. So before I proceed, I point out something that you might have noticed already. That is this term over here that is in front of the front of the operator. There's AK lambda, all of this stuff you might have expected from a harmonic oscillator and from a plane wave, right? When you expand some electric field in a plane wave, you're going to get some coefficients A times e to the I k dot r. That's just like a Fourier transform. And then all we have done essentially is take the A and make it into an operator in the quantum picture. Now, as I mentioned, there are a lot of steps. You can't do it just arbitrarily. If you want to be careful, you have to start with the vector potential and quantize it. But that's what the handout shows you how to do. But at the end of it, we have seen that there is this term that is sitting in front, square root h bar omega divided by 2 epsilon naught v. And if you think back to an earlier lecture, if you remember, I said one of the ways in which we can determine when things are quantized and when things are classical is to look at the energy in a photon, half h bar omega, and equate that to the energy in the electromagnetic field. Right? So the energy in an electromagnetic field is this half epsilon naught v times E squared, and I equated that to half h bar omega, or you can say that, actually I take it back, I'm sorry, I think the energy of a photon is h bar omega, and then there was no factor of half because there's both the energy in the magnetic field and the electric field. So this ended up being just epsilon naught v over e squared, or maybe there was a factor of half. It doesn't matter. The point is the E, as we saw, becomes square root h bar omega over epsilon naught v. And the factor of half and stuff is not important anyway. The point is that the photon electric field, simply by the simple argument of equating the energy in the electric field or the electromagnetic wave to the energy of a single photon h bar omega, gives you this factor h bar omega by epsilon naught v, and that has shown up again in this derivation, h bar omega divided by epsilon naught v with some factor of square root of 2, which is not so important. So we see now that in fact that simple argument is also accurate in the quantum picture. This is the approximate, or this is in fact now the electric field of a single photon. Okay, this is how you would find it. The V, of course, is some quantization volume that we expand the system in the normal modes that we have to put in a box and so on. And that, of course, depends on the exact situation that the electromagnetic field exists in. Okay, and so now let's think about another situation that is very common. So far I wrote down traveling wave solutions of the electromagnetic field. So that is this derivation. Don't need all that anymore. Right. So instead of thinking about this electromagnetic field as running waves, we can also ask about what happens if we expand it in terms of standing waves, right? So then there might be a factor of 2 that arises because sines and cosines are not normalized to 1, right? I mean, because sine squared, average of sine squared x, for example, is 1/2. Okay, so we might have another factor of 2 then. So let's just look at a single frequency. Let's just consider one frequency. Omega k equals, say, some nu in one dimension. Okay? Almost everything we need to understand about these kind of normalizations can be done by just looking at what happens in one dimension. Then the positive frequency term of the electromagnetic field that I just erased can be written as h bar mu divided by 2 epsilon naught d times a1 e to the I kz plus a2 e to the minus I kz. Right? This is exactly ak and a minus k. Okay? And ai and aj dagger R is equal to delta ij, and E minus is equal to E plus the whole time. Okay? So we can write the same traveling wave field operator in terms of standing wave modes by considering some new variables, A, C, which is A1 plus A2 divided by square root of 2, and AS, which is equal to A1 minus A2 divided by square root of 2. So if I substitute that over there, I get E plus is equal to square root of 2 A over nu plus 2 epsilon naught V times AC cosine of AC plus AS sine of AC. Okay? And you can verify, so first of all, of course, you see this factor has changed a little bit. Now you have a square root of 2 that appears, which comes from this normalization of the cosines and sines. And the other thing that you see, these AC and AS, you can check that they also obey bosonic commutation rules, and then you can verify that the Hamiltonian for the system will now be AC plus AS dagger AS plus 1. Okay. So if you have, for example, a standing wave mode, when would that be natural is when you have, let's say, a cavity, right? If you have a cavity, you don't want to expand in terms of traveling wave modes, which are the e to the ikr. You may want to expand in terms of these standing wave modes, cosines and sines. Then you would have this kind of Hamiltonian in one dimension. You can generalize to 3 dimensions. The other cases, for example, like in a transmission line, resonator or things like that. Any place where you want to look at waves that are not traveling, then this might be a more natural choice. We will use both of these interchangeably, just we have to watch out for these factors of square root of 2 and so on, especially if you're going to worry about things like the rate of spontaneous emission and so on and so forth. Okay. You can also, of course, find the magnetic field. So far I've been working with the electric field, and you can also calculate the magnetic field from the original operator A, which was the vector potential, then B is just del cross A, so you can go back and look at how that would affect the magnetic field, but then you can also write that down for an electromagnetic wave, and from that we can go further, right? Because once you can write down both the electric and the magnetic field, you can start thinking about lots of things for the photon, including things like momentum and linear momentum and angular momentum. Both of those can be calculated for an electromagnetic field in this quantized picture, and I'll give that as a homework with outlining the steps, because there's obviously a lot of algebra. So now that you've done one of them, you can do some of the others pretty straightforward. Yeah.
So I see like for the different dimension of the A1 and A2 is AK and A minus K.
Yeah.
Is there any relation between these two operators, like AK equal to minus A minus AK equal to A minus K? Like what's the relation between these two operators, AK and A minus?
I mean, the relation is that, right? AI, AJ daggers, delta.
Yeah. I mean, when you define the AK and A minus K, it's like one is along the one direction, one is along the
right. Exactly.
Oh, I see.
Yeah. Exactly. So AK corresponds to the traveling wave that's going positive and negative.
Okay.
That's what you do. Before I proceed into discussing states of the electromagnetic field now, so like we can ask ourselves, now that we know what the operators are, we can ask for the corresponding eigenstates and what kinds of eigenstates we can construct and so on. Let me briefly talk about the photon wave function. So we have already probably, to some extent we might say, well, once we have the electric field, right, for the electromagnetic field, the electric field must be something related to the photon wave function, and that is sort of true, but we have to be careful. Okay. as I'll show you in a minute. So originally when people first started bringing about quantum mechanics, and this may have been something that you wondered about when you learned undergraduate quantum mechanics, you might have thought, okay, so I know about the wave function for a normal particle like electron or something. I just write psi of RT, which represents the probability amplitude for the electron to be found at the position R and at the time t, and I take the square of that times some volume, then I get the probability to be in some small volume around R and t, right? So can I write something similar to that? So the obvious solution would be, say, well, take the electromagnetic field E of RT and say that that is corresponding to the the corresponding probability amplitude for a photon, and that was the first thing that people tried. So Kramer of he first came up with this idea that electric field, or people generally, famous people thought, well, yeah, that should be it. Electric field is the equivalent of the Schrodinger wave function for a photon. But he pointed out that the solution of Maxwell's equations will have both e to the plus I omega t and e to the minus I omega t. Right? When you look at the Maxwell equation solutions, they'll typically have both of those, just like we did here. Right? I mean, if you write this out, there's a e to the minus I omega t and the e to the plus I omega t. And so he said that those are not eigenfunctions of the standard Schrodinger equation, which goes as I dou over dou t. You're going to have both plus omega and minus omega. You cannot construct a true solution. Well, anyway, so that was the problem. He showed that you can't just take the electric field and equate it to the Schrodinger equation. So there must be something different. Bohm came up with another idea, which is that the probability of finding the light quantum in some region dx around the point x is just given by the square of is given by the energy of the particle. So what Bohm came up with was that you can equate the energy of the particle divided by the number of photons, or the energy of one quantum. That gives you like a number of photons at the position x, and so he can equate that to the probability. So he just said, okay, p of x dx, which is the probability density, p of x is equal to half epsilon naught times e squared plus h squared divided by h bar omega of x times dx. But you can see this is a problem. This just talks about the probability, doesn't say anything about the wave function itself, which you might need in some kind of interference experiment, for example. Okay, so there was no real good definition of what the wave function of a photon should be, and until you come to the second quantization picture. Okay, so it's kind of interesting that for the photon, at least, to get to the definition of the wave function of a photon, you kind of have to quantize the electromagnetic field, the field itself, and then come back and define the wave function of the photon. So I'll just remind you, in second quantization for massive particles, so this also, was not right. This is Bohm's definition. Okay. So if you go back and look at second quantization for a massive system like mass m, like say electron, for example, then the wave function of an electron is written as psi of RT equals sum over p Cp e to the minus I Vpt times phi p of R, right? And So this is of course just a Fourier transform for a regular particle, right? So if I take the wave function of a particle, of an electron, I can write down its Fourier transform in terms of these coefficients, Cp times phi p of R, where say, for example, you could have chosen phi p of R is equal to some 1 over square root of v e to the I p dot R, right? So when that's true, then these are like, say, the running wave solutions or traveling wave solutions for the Schrodinger equation. You put them in here, and you can expand, and you can get the wave function of the particle. And in second quantization, what we do is we take this Cp and we make it an operator, right? That's what we do in second quantization. And the Cp, if it is a boson, we say that the Cp must obey Bose-Einstein commutation relations, and if it is a fermion, then it must obey Fermi-Dirac commutation relation, anti-commutation and commutation relations. Okay, so this is how we proceeded with second quantization of a system, a massive particle, from which we then obtained the quantum field theories, right? So quantum fields. The quantum field theory says that psi of RT, which is now an operator, is the summation over all the possible states, Cp, where Cp is now an operator, e to the I mu pt times phi p of R. And this Cp then is the operator that creates a massive particle at the position r at time t, which will have the corresponding wave function which is expanded in this basis state of phi p, and in general the size then that is the state of the system is some summation over all n1, n2, etc. with some amplitudes n1, n2, etc. with the basis states that correspond now to occupation numbers in the different states P. So this is N1, N2, etc. are occupation number representations. These are all vectors. So that's how we did quantum field theory for massive particles. And the wave function of the massive particle system can then be written down. For a massive particle, the wave function now in the second quantization picture, psi of RT is just taking this quantum field, which is an operator, R comma T, and acting on the state ket psi of T, which is this, which is given by this guy, and which can also be written as equivalently creating from the state vacuum by the psi dagger operator on this is the vacuum, and then projecting it onto the state ket. So if I take the state of the system and write down explicitly what this will be, this is sum over all possible occupation numbers n1 and n2 times n1, n2, etc. Fn1, n2 star, star of n1, n2, summation over p, Cp dagger e to the I p times phi p of R acting on the state 0. Okay, so that's the full representation. This can only be non-zero then because of Cp dagger, right? Cp dagger can only be non-zero when it acts on this guy if only one of the indices Ni is equal to 1, right? Because otherwise it will vanish when you try to take the Cp dagger on this and project it onto the vacuum. So this is non-zero when one of the indices in I equal to 1. So then psi of RT summation over I S star 0 0 sum 1, where 1 is for the ith state of the system, phi Ei of R times e to the minus I mu t I. Okay, so this is how the wave function for a particle should be written in the second quantization picture for a massive system. Okay, starting from the quantum field description. And so in the photon case, we have arrived already at the quantized field picture. We have quantized the field of the electromagnetic field. We have written down just now the electromagnetic field in the second quantization picture. So by analogy, we should define the wave function of a photon in exactly the same way. Okay. So, for example, if you took a single field, or let's just take the a field which is for and if you think back to the quantization of the electromagnetic field, as I said, we came up with two parts, the positive frequency and the negative frequency part, and it was the positive frequency part which had this state. Hold on, in a second. So by analogy, we define wave function of a photon as psi, I'll just put E down here to represent the electromagnetic field, is 0, and now I'm going to choose the E plus, which is the one that has the annihilation operator in it, and that is the positive frequency term in the electromagnetic field, psi of E. Okay? Or if I go back and put that in, you'll see in a second why this is true. So it is sum over k lambda. I put back the definition that I already had for the electromagnetic field, the positive frequency part, which has the ak lambda dTi k dot r minus mu kt times psi. Okay? So this is a single photon field that is sharply peaked at the frequency nu equal to omega. Okay? So for example, if I have this, that I can write that as square root h bar omega over 2 epsilon naught 0 . So here what I'm basically doing is I'm assuming that there is not a strong variation of the field with frequency, so that this nu k, or you can think about it as like the density of the states or whatever you want to call it, if I were thinking about the spectrum of the field, right, it's almost, the density of states is pretty closely peaked around nu k, so that I can just have some small spread in the field, but the nu k part is almost equal to omega. Okay, so this is omega, and so the various modes of the electromagnetic field almost have the same energy or same frequency omega. So I can put that in there. There's some small spread. Like you can think of this as some, instead of an integral, you can think of it like some. Instead of a summation over the infinite plane waves, it's just a summation over a few or over a small amount, and then there's ak, times. Now, this is just the one photon field, K. Okay? So this guy here is the equivalent phi of R comma T for a single photon. By analogy with what I wrote down there for a single electron or single other boson field for the massive particle case. That is, okay, if you want to follow exactly the same analogy here, distribute as summation. Right? So there's a 1 in just the kth mode, just like we had a 1 in the ith mode, phi p of r, which now is this ak of r, which is the operator, and then that is acting on the state. Okay. Either way, both ways are, oh, this is square root of. This is the equivalent of this phi p of r. E to the minus mu p of t, which is still over there. There's a polarization, of course, because these guys have polarization states, and yeah, that's our state over here. Because this is the state 0 ak 1k. That matrix element is 1. So I just remove that also, right? Okay. So for a single photon field. We can also rewrite the Maxwell equations in terms of these single photon fields. I will leave that, I'll put that in the handout, but it's not very something again that we use a lot, so I won't really put that in here. So that's it. So that's kind of our discussion of quantized field and how the wave function, the photon wave function, can now be derived from this quantized field. But now, instead of worrying about the photon wave function, because it turns out that photon wave function is not a very useful thing to think about, unless in some very specific cases, we are now going to talk about states of the electromagnetic field. Okay. The reason is what we want to do, thinking about it physically, right? So you have some classical light beam coming in, let's say a laser or something like that, or you have some train of pulses from some source, and you want to think about how to describe the state of the electromagnetic field. So the obvious way to do that, okay, so let's first talk about the intuition, right? And then we'll describe the two different ways in which we think about this. So I take my light source, okay, and I put it on a detector, okay, and I look at the output coming from the detector, okay. This is the plot of, say, voltage or some other signal versus a function of time. Okay. So if I take a PMT or an avalanche photodiode, which is a single photon counting module that can produce pulses for every photon that hits this object, then of course what you see coming out of this detector is a train of pulses. Okay. Etc. etc. Okay. So you might look at that. This is similar to, have you guys used a Geiger counter at some point in your undergraduate lab? Right? So if you took like some gamma rays or beta particles or alpha particles and you took your Geiger counter, you hear individual clicks coming from the Geiger counter. Okay? The Geiger counter is clearly showing you that the particles that are hitting it are coming in quantized. Okay? So that might be it, right? If you say, hey, I took my light beam, right, and I shine it on a detector like this, and I get pulses. So that's just like a Geiger counter. Light is quantized, end of story, we don't need to worry about this, right? This would be the first thing that you could think of to show that light is quantized. For example, this whole treatment that we did was we quantized the electromagnetic field, and now I'm saying how do I experimentally determine that the light field is indeed quantized or not, okay? The problem with this description is that what is happening inside the detector is also a quantum process. So you could have a purely classical wave coming into the detector, and then inside the detector, maybe you have a quantum object, like say an atom, which is interacting with the electromagnetic field, and maybe it's the atom that's producing individual bursts of electrons. Okay? How do you distinguish between these two situations? Okay, that's the first question we can ask ourselves. How can we describe the difference between the state of the light beam and the state of the detector, or the effect of the detector on the light beam and the product that we see in the lab, which is the output voltage pulses that are coming out of the detector? Okay? So what we're going to do is first we're going to focus only on the electromagnetic field part. That is, we're going to look at the electromagnetic field, and this we already quantized it in the second quantization picture. So we can definitely think about all the possible states of the electromagnetic field in this quantized picture. Okay? So that is the first part, and that's what we will describe first. Okay? So that's what I'm going to do now. But then the next question, as I just explained to you, is I can ask, how does that compare to what you see in the experiments, and how do you distinguish between the different states of the electromagnetic field, this quantized electromagnetic field, from the experiments? So those are the two separate things that we have to keep in mind in this next discussion. So first, I'll simply talk about very abstractly what are the possible states of the electromagnetic field. Well, it won't be super abstract. I will try to make some connection to physical pictures. But then you also have to ask, what happens experimentally? How do I distinguish, and what does it look like in an experiment when I shine different states of light onto a detector? How can I distinguish between them? And so the first way in which people were distinguishing between them, let me just give a sort of broad overview of this, is simply to look at the statistics of the photons that are coming out from this, of the pulses that are coming out from the detector. Right? By statistics, I'm sure you know what I mean. I take some time interval delta t. Okay, I divide up the time into, they say, uniform intervals. For example, that would be the simplest thing. Okay, I measure the number of photons or clicks, pulses that I get in each individual time interval, and I plot a distribution. Right? And that distribution. So, for example, I might be looking at this click. So, in say bin 1, I get 1. In bin 2, I get 1, 2, 3. 1, 0, etc., etc. I'll get the statistics, and I plot a distribution. And the distribution, if I plot the probability of some n, where n is on the x-axis, and the probability of n is how many of those divided by the total number of events, I'll get some distribution. Okay, some histogram. Okay. Maybe it looks like this, maybe it looks some other way. I'm not saying exactly what it looks like, but you all probably know what it is, right? What is the typical distribution I'll get for counting photons or counting radioactive particles from, say, a Geiger counter or an APD or something else? What do you expect? Have you heard of this distribution? Huh? Gaussian. Okay. Poisson. Okay, we have two choices, Poisson or Gaussian. Which one do you think will be the real case? Okay, so in fact Poisson is correct. And the only reason I said Poisson is correct is because that is the accurate description even when the average number of photons in each time interval is very small. Now if the average number of photons, the counting rate is very large, then Poisson and Gaussian become almost equivalent. Okay, so that's why sometimes we cannot distinguish between Poisson and Gaussian in an experiment. The Poisson and Gaussian will have nearly the same looking distribution when n the number of photons in each interval, or lambda, which is the number of photons times the time interval, is very large. Okay, then they approach each other. Okay, with the standard deviation sigma is equal to the square root of the n bar. So this is Poisson distribution. P of n will be Poisson, and the main sort of result from that, I want to write down the Poisson distribution. We'll come back to it in a minute later, but the point is that the standard deviation of the Poisson distribution is equal to the square root of the mean number of photons, right? So if you calculate the mean of the photons and then you calculate the standard deviation, they are related by this square root behavior for a Poisson distribution. So again, this is a very simple sort of description of what photon statistics is. This is what you can do in the lab, right? You shine some beam on the detector, look at the pulses, make the statistics, and that's what you can typically do in a simple experiment. Okay. So what I'm going to do, as I mentioned, is first I'm going to discuss what are the possible states of the electromagnetic field, okay, and the types of behavior. Before I go on, so Poisson has this kind of behavior, right? But there is another way to describe this, which is we can write down different classes of light sources could be described as Poissonian, where sigma is equal to square root of n bar. Okay, then super Poissonian, sigma is greater than square root of n bar, and sub Poisson, sigma is lesser than square root of n bar. And all of that is essentially saying something about the width of this distribution, right? So Poisson is exactly sigma equals the square root of the average value. Sub-Poissonian will be when the distribution is narrower than you would expect from a Poisson source, and super Poisson is when the distribution is wider. Now, it's very easy for anyone to construct a source that is super Poissonian, okay? Because remember, one of the assumptions in the Poisson distribution is that there's a mean counting rate that is constant throughout the experiment, okay? So for example, no matter what time interval I measure, there is the same counting rate in lambda, right, which is representing the count rate of events arriving at the detector, okay? So that lambda times say delta t is the number of photons that arrive in that particular interval. This is the standard assumption for Poisson, and this lambda is supposed to not fluctuate at all throughout the experiment. So obviously if I took, say, some source like a discharge lamp or whatever, and I can easily construct super Poissonian source by simply making the voltage to the discharge lamp vary with time, right? In some random fashion, or there could be other sources of light in the room that are interfering with your experiment. There are any number of ways in which I can make a super Poissonian source. But so it's easy to make super Poissonian, and it's fairly easy, as you will see, to make Poissonian sources. It is very hard to make the sub-Poissonian sources, to make the fluctuations narrower than in the case of the Poisson. Okay? And that is the key of why we can use photon statistics even to understand that light must have a quantum nature, because it will turn out that sub-Poissonian sources can only be created when you fully understand the quantum nature of light. Okay, so that is the first sort of smoking gun evidence that light is indeed quantized. You may not question this at all, right? I mean, people now are all used to thinking that light is quantized and so on. But I'm talking about, like, if you didn't know that, or if you didn't believe that, how would you convince someone, right? So if some undergraduate comes to you in the lab and says, I don't believe that light is quantized, how are you going to show them that light is indeed quantized? Okay? This is one of the ways in which we can argue that light is indeed quantized. Okay? By the sub-Poissonian statistics. You can convince them that it's easy to make Poisson and super Poisson with classical sources, but only really quantum states of light will give you the sub-Poissonian statistics. Okay, so now let's discuss these states of the electromagnetic field. And you may already be aware of some of them, so I'll try to go through that fairly, I think it will be fairly straightforward to go through them. Before I do that, I do want to introduce one other concept that we've kind of skipped until now, which is called the density operator. That will turn out to be useful also when we discuss the electromagnetic field, and also when we discuss interactions of the So this is sort of like a reminder. Probably many of you have seen density operator. Have you seen density operator in graduate quantum? Yes? Okay. So I'll go through this fairly quickly. Normally until now we have said the state of a quantum system is represented by the state vector psi, right? Which is a ray in Hilbert space. Okay? But this is not useful for many practical situations, and we certainly cannot treat like macroscopic objects with just a simple state vector. So we introduce a density operator, which is that suppose the system is not in a pure state, as we call it, just one state vector, but can be in multiple quantum states psi alpha with some probability P. Then the density operator rho is defined by summation over alpha, P alpha, right? And this is an operator, clearly, because you need to sandwich it between two other state vectors to make it into a number, okay? So it's like a matrix. So, and if there is a basis phi, in which rho is just simply if rho is equal to just phi, and maybe you can find this by some unitary transformation, some transformation that exists that takes this guy into this guy, right? If that is true, then we say that the state is in the system is in a pure state, okay? And if it cannot be found, that if such a basis transformation cannot be found where rho is equal to phi in this way, then the system is in a mixed state. Also, if the off-diagonal elements of rho vanish, then the density matrix rho has purely diagonal elements, which means that we can write this as what we call a statistical mixture, okay? Which means that we can simply think of it as the system existing in any one of these states, say 1 through n, with some probability p, okay? And so that's like saying that I don't know much beyond some probabilities, so that's called a statistical mixture, okay? So let's take, for example, the simple case psi is C1 1 plus C2 of 2, C2 times 2, this is for a 2-level system. Then rho, which is in this psi is equal to simply C1 squared 1 1 plus C2 squared 2 plus and from this definition, from all these definitions, and for example this particular case, we can derive following properties of the density operator. These are very important properties that any real density operator has to satisfy. So, must be Hermitian, the trace of rho over all the possible basis states must be equal to 1, and the third property is rho squared must be lesser than or equal to rho. Okay, that is that if I project this onto any two pure states, that this must always be less than the density matrix element in that state between those two states M and N. Okay. We can also calculate operator expectation values directly from the density operator. So if, for example, we want to find out the expectation value for, say, position or momentum or some other operator that we want to find out, then S, the expectation value for that operator, is simply summation over alpha, P alpha times psi alpha. Right? Just you take the expectation value given by quantum mechanics, and then you multiply it by the probability to be in the state psi alpha and sum over all the states. Okay, and you can just show after some steps that this is the trace of the density matrix with the operator S. Okay. And I already mentioned this, but if you look at for the two-level system, then the diagonal elements, one, that is the rho 1, 1, right? This is rho 1, 1 here. And rho 1, 2, or rho 2, 2 over here. These correspond to the probabilities to be in the state 1 or state 2. Okay? Because modulo C1 squared and modulo C2 squared represent the probability to be in the state 1 or 2. But that could have been described even classically. I could have just given you a system like a coin, and I flip the coin and I say half of the time the coin is in state 1, half of the time the coin is in state 2. That's a bit, right? But what's the difference between a bit and a qubit are these other terms, the off diagonal terms, okay? Because that represents the possibility of interference between the two possibilities 1 and 2. So these are the coherence. Rho 1, 2 and rho 2, 1. Sorry, this is rho 2, 1. And of course, the way I'm defining these is rho n prime is equal to n rho n prime. Okay, so rho 2, 1 represents this 2 rho 1, which is this element over here, C1 star. C2 is the coherence between the state 1 and 2, and you can see that that is just the complex conjugate of rho 1, 2 because rho is a Hermitian matrix. Okay, so all this you're probably familiar, but it's useful. So these are the coherences, and these are what we call populations, or the probabilities to be in state 1 n. Okay. And from the so this rho squared lesser than or equal to rho, this property we see that rho ij squared is going to be always lesser than or equal to rho ii rho jj for arbitrary mixed state. So this tells us something about the way to check if a state is if a density matrix is in a mixed state or not is by calculating these amplitudes of the coherences, the square of the coherences, and comparing them to the product of the probabilities. So this must always be true for any mixed state, and it will be exactly equal to rho ii rho jj when it is in a pure state. Okay, which you can also verify from him. Okay, so that was it. Just a quick reminder about density operator, because now we will use that when we look at the electromagnetic field. Okay. So now going back to the quantized field picture for electromagnetic waves, we'll just write down again the operators. E of r comma t is summation over k lambda I'm from now on skipping the second part, that's just the Hermitian conjugate of the first part, and H is summation k lambda H bar omega k. So what is the state, which is the eigenstates of these fields? Well, you can see it's a very complicated looking state. It is the state which is what we call a Fock state. Okay. These are the basis states of this electromagnetic field, right? Of this Hamiltonian, basically, which are given by there being possibly n k1 lambda 1, which represents essentially that there are, say, that many photons in the mode 1, then there could be some other set of photons in the mode 2, up to some kr lambda r. So that is one possible basis state, which is essentially governed by k lambda 1, the operator, which is raised to n k1 lambda 1 divided by square root n k1 lambda 1 factorial, etc. up to a kr lambda r dagger raised to n k r lambda r factorial, acting on the vacuum. Okay, which of course satisfies that when the annihilation operator acts on the vacuum from any mode that it is creating, it is annihilated, it's zero. Okay. Okay, that's the definition of the vacuum. So you see that these states are extremely cumbersome, right? Just thinking about like a simple eigenstate, a Fock state, already it requires you to write down this enormous sort of set of states which has all of these modes in it, and write down the occupation numbers for each of these modes. So typically what we'll do is we'll consider just a single mode, okay? Because most of the things that we are going to talk about when we want to understand the properties is enough to consider one mode of the electromagnetic field. And that can be either a traveling wave mode or a standing wave mode. But so all we'll do is consider one mode, because that's what is easiest to think about. Of course, if you want to do the derivations for multi-mode fields, you have to go back to this original representation. Okay? So that is usually something that's done in the advanced quantum optics textbooks. So you can, I'll give you some reference if you are particularly interested in multi-mode fields. These have been done in like old papers and also in some of the textbooks when you come to like specific things that need the multi-mode fields. Okay. But what we'll do is just focus on a single mode, because most of the physics that we are interested in is understandable with just thinking about a single mode. Okay, so I already introduced one such a state of the field, which is the Fock state. And the Fock state, as you can see, is given by this state of the field. So now let's consider one single mode case. The single mode electromagnetic field is, of course, the same thing, but now just with one guy. We got the I k dot r minus omega t. So I took the one traveling wave mode. So I got A and A dagger minus I k dot r minus omega t. And I've also considered only one polarization for this state. So it's just got one traveling mode with a certain polarization, and that is the electric field. And for this guy, of course, it just looks like a harmonic oscillator. The Fock states are given by A dagger n, 0 by square root of n factorial. And in this Fock state basis, then of course everything is easy. A dagger A is equal to this guy. A acting on the state n is square root of n minus 1. A dagger acting on n is equal to square root n plus 1 acting on n plus 1. Okay. And n is just equal to this A dagger A is the number operator for the field. As I said, this is, easy to write down, extremely hard to do experimentally. Okay? Alright? Because even when you think about, let me take a simple case of a laser that is propagating in free space. The laser, by definition, let's say, unless it's an infinitely broad laser which is extending across, say, the universe, right? It has been confined to some spatial volume, spatial mode in the transverse dimension, right? Or even if it's confined on an optical table, it's confined inside your room, so it's within some box and has some finite transverse dimension, which means in this traveling wave basis, it already has several modes, right? Because the traveling wave basis is a uniform wavefront which extends from minus infinity to plus infinity, right? That's the traveling wave mode basis. With some box, okay, V, but the V is supposed to be extremely large to take into account, that you can do all these operations like integrals and so on, and orthogonality and so on. So already we are making the assumption then, and of course there are cases where it's a good approximation, where you can say that it's almost like a single mode, but it is an approximation. Okay, you're basically assuming that you can create this sort of single mode state and work with it. Okay, and that can be hard, as I just mentioned. Okay, all right. So and obviously the Hamiltonian H acting on this n is simply H bar omega n plus half acting on it. So it looks just like a harmonic oscillator, and it is a very simple treatment according to the same harmonic oscillator eigenstates and all the usual things that happen in our mind. And I should point out again, I have not said anything, this is at an abstract level, I have not said anything about how you create these Fock states. Okay? It turns out, once again, creating Fock states of the electromagnetic field is extremely difficult experimentally. Okay? Well, whichever frequency regime that you're in, optical, typical optical frequencies, microwave frequencies, etc., we will show in a bit that the easiest fields to create are what are called coherent states or thermal states. Okay? It's very hard to create these Fock states. Okay? These are Fock states. Okay? Because basically I'm saying I'm creating a field which has exactly n photons in that mode. And if you think back to that earlier thing that I told you about Poissonian statistics, this is obviously extremely sub-Poissonian. It has no distribution at all, right? The probability is exactly 1 to be in the state n and is 0 outside of n, right? So that's a perfect sub-Poissonian source of light. And this is highly quantum. And it's very hard, therefore, to create such quantum states of light. Okay, I'm going to stop there and we'll start we'll talk about this in the next one. I've graded most of your homeworks. I'll get them back to you next week. That's why I didn't assign any new homework yet. Once I finish grading and putting the grades up there, I'll assign some homework. New homework, sorry. Yes. Any other questions, by the way? Sorry. Okay. Fine. Okay.
So like when you talk about logical,
Yes.
this is like the real quantization of the electron.
Yeah.
Like so there's a lot of people in
Yes.
like different frequency, different data.
Exactly.
But like how do you like make sure like in the real experiment the other mode will not like have any impact on your like single mode approximation here? Like
how do you make sure that you won't have any impact?
yeah. I mean
I guess the only way you can do it is through experiments, right? Meaning you try to create the conditions for a single mode, and then you carry out the experiments that prove that you are clearly having a single mode quantized field, and if it works, then you know, and if not, you say, well, there must be some other modes in there.